To talk about the binomial distribution. So remember our distinction between discrete and continuous quantitative variables. Discrete variables were counting, they were distinct points on a number line. So the binomial distribution is a really specific type of discrete distribution. And specifically, you can think of this as counting up the number of successes in a particular number of trials or observations. So counting up successes in n trials. That's sort of our real short way of thinking about this binomial distribution. So it's discrete because it's distinct, counting up how many successes, 0 successes, 1 success, 2 success, all the way up to all n of them are successes. Now we do need to be a little more specific and careful about that definition. So that's what follows next. Make sure you know this acronym and you can write this out. Don't just write this BINS. That's not good enough. I think my small children could probably do that. So make sure you know what each of these stands for. So let's go through these. So for example, suppose I'm going to toss a coin 10 times and count how many heads I have. So example, toss coin 10 times and count number of heads. Okay, that would be an example of this binomial type discrete variable, because it meets these 4 criteria. The first one being binary outcomes. By binary, we just mean that the outcomes can be classified as a success or a failure. So in this particular example, my success would be heads. That's what I'm trying to count up. And my failure would be tails. The next item here that must be met is our trials need to be independent, meaning in our case, one coin toss doesn't influence the other. So I'll just say that here, one toss does not influence the next. So sometimes this requirement of independent trials is obvious, like tossing a coin or rolling a dice. If you're dealing with human subjects, for example, though, might not be as obvious. The way we meet independent trials is if we collect a random sample. We talked about doing that earlier in the course. So random sample, each one is equally likely to be selected, so each trial is not going to influence the next. Then we need to have n, a fixed number of trials before we begin the experiment. In our example here, our fixed number of trials would be 10. I have n in parentheses here because to state that the criteria is satisfied, just say what n equals. Then we need to have the same probability of success for each trial. In this case, the probability of success is 1/2 or 0.5. By same probability, I don't mean success and failure are both 50-50. I just mean if I toss the coin one time and I've got a 50% chance of success, the next time I toss it, that success stays the same at 50. It's not going to change my chance of success each time I do the experiment. Whatever it is, it stays constant. So if you can meet all 4 of these criteria, then we are allowed to say x, our random variable. So for example, up here, I might define x to be the number of heads. X is this variable that's going to count up the number of heads. So it met those 4 criteria, and I can use this shorthand notation, this counting variable. This little tilde is read can be modeled by. Then we're going to say binomial. And you might see other places, they might just write BIN or B for shorthand. I'm going to write it all out, but those variations are also used. And you need to give two pieces of information to define this. N, how many trials you're doing, and P, your probability of success for each trial. So that's our binomial distribution. If you can determine that just one of these four is not met, then it's no good. It's not binomial. All four must be met for us to be able to use a shorthand notation and say x, this counting variable, is binomial. So let's check out a few examples verifying if these are binomial or not binomial. So first one here, x, number of times snake eyes are rolled in a game of dice with 10 rolls. So let's write down our acronym, BINS. But don't just, that's our starting point to help us out. Let's write what each thing stands for. B is binary outcomes. I is our independent trials. N is our number of trials fixed ahead of time. And then S means we have the same probability of success. So again, don't just write down BINS, write down what each one stands for. And then in our particular experiment, our binary outcomes are we get snake eyes, which by the way is you get a 1 on each of those die. So snake eyes, a 1 and a 1, or not. Every other combination is our failure. So success, we get the snake eyes or everything else. Independent trials, sure, one roll does not influence the next. That's kind of understood here. And then our fixed number of trials, they tell us we have a game with 10 rolls. So that is definitely met. Our N is 10. And then last but not least, our probability of success. Dust off your probability formulas here. Chance of getting a 1 on the first die should be 1 out of 6. And means multiply. The chance of getting a 1 on the second one, 1/6. So the multiply 1/6 and 1/6, you get 1 out of 36 is our chance of success. So it meets all four criteria. So we can go ahead and say x, this variable that counts up number of times we get snake eyes with 10 rolls, is binomial. And the order you put these down is important. The first thing needs to be our N of 10 trials, and the second thing needs to be P, our probability of success. So we can write all that information down with this shorthand. And you don't even need to put N equals and P equals. If you just put the numbers in here, it's understood what those are representing. Okay, next one, number of shots it takes for a player to make 10 free throws. I'll let you think about this one for a moment on your own. Pause and go through those criteria. All right, hopefully you're thinking not binomial. Remember, for it to be not binomial, it only takes one thing to throw the whole situation off. So, not binomial. Let's think through our reasons here. Binary outcomes. They're either going to make or miss their shot. Independent trials, that can be debated on the level of the player. So maybe that's your reason of maybe the trials aren't independent. Maybe if you're like me, you're going to adjust and hopefully get better as you go. Number of trials fixed. This is one we can all agree on, is that is not met. We know we want to make 10 free throws. That's when we're going to stop, but we don't know how long that takes. If it's me doing this, it's only, we could be here all day long until I get 10. If this was LeBron, it wouldn't take any time at all to get those 10. So, number of trials. Is not fixed. So again, if you can fully justify one reason one of these 4 criteria being unmet, then the whole thing's off, not binomial. Okay, think about this last one on here. The number of children in a family of 5 that get the flu during a given year. Right, this one is also not binomial. And our reason, if we're talking about a family of 5 children, then if one gets sick, probably it's going to spread around all the other children. So this would be a very clear case where we do not have independent trials. So I'll just make that comment. Trials are not independent. All right. So this has been our setup for identifying and verifying that a counting variable is in fact a binomial variable or follows the binomial distribution. And we're going to add on to this in the following videos.